All right, so what we're looking at today is something a little bit different, and it's called the logarithmic function or the log function. Now, this might be a button that you've seen on your calculator where it just says log. You've always wondered what it means. Well, we're going to look at that today about the log function and how it is used or how it is present in our daily lives. And so what I have here is a bunch of x values. We have 1,000, 100, 10, 1, 1/10, 1/100th. Now, if you were to take out your calculator and hit the log or put 1 in and then hit the log button, your answer would be 0. Now, if you take the log of 10, and if some of you have your calculator out there, you can do that. Take the log of 10, you actually get 1. And if you take 100 and you hit the log button, you get a 2. Well, you can hopefully maybe see the pattern, but if you take the log of 1,000, you get 3. Now, if we go the other way and you look at 1/10, which as a decimal actually is 0.1, and you take the log of that number, you get -1. And if you take 1/100th, which is 0.01, and you take it to the power of, or you take the log of it, you get -2. And so what the log function is doing is it counts the number of zeros that you have left or right of the decimal. So 1, well, there is no decimal. There's no zeros. So you get a 0. 10, you have 1 0. 100, you got 2 zeros. 1,000, you got 3 zeros. So if we had 10,000 and took the log of it, we would get 4. And so going the other way, you actually have a 0, 1 0 left of the decimal. So it's -1. In this case, you get 2 zeros left of the decimal. So you get a -2. The other thing I want to show you is that the difference between our x values here is that if you are going down this way, you're multiplying by 10. 1 times 10 gives you 10. 10 times 10 gives you 100. 100 times 10 gives you 1,000. And that's how the logarithmic scale works. The big thing is when it was used is back hundreds of years ago, before calculators, they couldn't use big numbers. So what they had to do, they had to figure out a way to take a big number and shrink it down to a much smaller number. And so they did that by basically counting the zeros. All right, now, how do we use this in our daily life? Well, we'll get to that, or how we might see it, or how it applies. Is to start off here, example number 1 is we have 3 earthquakes occurred in locations A, B, and C with magnitudes 4, 6, 7, respectively on the Richter scale. So A had a magnitude of 4, B a 6, and C a 7. Now the Richter scale, the Richter scale, there we go. Here it is. Here's our different earthquakes that we have. So we have between 3 and 4, there's minor. We have like 50,000 a year. As you can see, as we go down this list, the bigger the earthquake, the less that we have them, thank God. All right, now the other thing is you look at the Richter scale here. It only basically goes up to 10. It goes up by 1s. But here's the difference with the Richter scale, or it is a logarithmic scale. So here's how it works. Now, A, how many times stronger was an earthquake at B than an earthquake at A? All right, now A had a magnitude of 4. B had a magnitude earthquake of 6. Now, if I'm going to compare these two earthquakes, I'm going to draw a 4 here, then a 5, and then a 6. And the reason I'm doing that is because the Richter scale goes up by 1s. Now, if I compare a 4 to a 6, that's 1, 2 different jumps. But because the Richter scale is a logarithmic scale, every time we go up 1, it's 10 times stronger. So a 5 is 10 times stronger than a 4. A 6 is 10 times stronger than a 5. So because we're making 2 jumps, it's 10 times 10 stronger, or 10 squared. It's another way to look at it, or 100 times stronger. So in this case, a small print here, a 6 is 100 times stronger than a 4. Again, because the Richter scale is a logarithmic scale. Then we get to B. How many times stronger was an earthquake at C, which is a 7, than B, which is just a 6? All right, well, if I'm comparing a 7 and a 6, there's a 7, there's a 6. Again, a Richter scale goes up by ones. Well, if we're only comparing a 6 to a 7, there's only one jump. So it's only times 10. And so, well, a 7 is 10 times stronger than a 6. Then we get to C, where we're now looking at how many times stronger was the earthquake at C, which again was a 7 on the Richter scale, than an earthquake at A, which is a 4. Well, again, if I'm comparing the two, I'm going to start at 4 and go up by ones, because that's what the Richter scale does. All right, so we get 4, 5, 6, 7. And if I compare the two, I'm making 1, 2, 3 jumps. So that's times 10 every single time. And so 10 times 10 times 10 is 1,000. And so in this case, if I'm comparing a 7 to a 4, 7 is 1,000 times stronger than a 4. So again, if I look back at my Richter scale, you see a 4, to a 4 to a 5 is just a light earthquake, where a 7 is a major earthquake. It causes, because again, a 7 is 1,000 times stronger than a 4. Now, the other scale we're going to look at is the decibel scale. A little Canadian trivia here, named after the inventor of the telephone, who happens to be Canadian, Mr. Alexander Graham Bell. That's the Bell name for company. But here's the decibel scale, and you can see it starts at 0 down here, where it's you can barely hear it. Rustling of the leaves is a 10. And in fact, the decibel scale goes up by tens. You can see we go up to 40, and it only goes up to 140. And the reason it only goes up to 140 is that if you hear a sound louder than that, it pops your eardrums, which apparently is extremely painful. Sharp pain and then a whooshing feeling, I guess, apparently. And then you have to get your eardrum reconstructed, and I don't think you ever hear right after that. So it only goes up to 140, just like our Richter scale only goes up to 10, because we just haven't had an earthquake that strong. Doesn't happen. Not that we know about anyways. All right, so but the big thing here is the decibel scale goes up by tens. So now, which leads me to next up. According to that table that I just looked at, where I'm just going to give you the values anyways, but a rock music has a loudness of 120 decibels. An ordinary conversation has a loudness of 50 decibels, and whispering has a loudness of 20. How many times louder is an ordinary conversation than whispering? So our ordinary conversation is a 50. That's a terrible 50. And whispering is 20. Now, if I want to compare those two, again, I'm dealing with the decibel scale that goes up by tens. So I'm starting at 20. Then I got 30, 40, and then 50. And so again, it's a logarithmic scale. So every time I make a jump up of 10, I'm multiplying by 10. So times 10, times 10, times 10, and 10 times 10 times 10 is 1,000. We just had that one, actually. And so a 50 decibel sound is 1,000 times louder than a 20 decibel sound. All right, now, how many times louder is a rock concert than an ordinary conversation? So now we're comparing a 50 decibel sound again, and a rock concert is 120. So it's close to blowing out your eardrums. All right, so again, I'm comparing a 50 to 120. I'm going to need some room over here. So start with 50. Then we got 60, 70, 80, 90, 100, 110, 120. And so now we're making 1, 2, 3, 4, 5, 6, 7 jumps. And each of those jumps we're timesing by 10. So I could say 10 to the power of 7, because that's 10 times 10 times 10 times 10 times 10 times 10. Yikes, times 10, 7 times. Which equals, let me see here, grab my calculator. I don't know what happens when we take 10 and multiply by itself 7 times. I end up with 7 zeros. Of course, that's the log. Which is, let's see here, 10 million. Yikes. All right, so a 120 decibel sound is 10 million times louder than a 50 decibel sound. That's why an ordinary conversation doesn't hurt your ears, and a 120 decibel sound, an ordinary conversation or a rock concert can hurt your ears, because a rock concert is 10 million times louder than a 50 decibel sound. All right, now we get to how many times louder is a rock concert than whispering? Yikes. So now I basically have my same table here, but whispering is a 20. So I'm just going to add in a few numbers here. So let's see, a 40, 30, and a 20. And so now we're making what we had 7 jumps from 120 to 50. And then we got 1, 2, 3 more jumps. So that's 10 times 10 times 10 times 10 times 10 times 10, multiplying 10 by itself 12 times. So that means I'm going to have 12 zeros. And that number, let's see here, 12 zeros. So I put a 1 and then we go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I don't even know what that number is. Let me see here. We get into millions, trillions, or billions, trillions. 1 trillion times louder. So a 120 decibel sound is 1 trillion times louder than whispering. Than a 20 decibel sound. And there we go. So that's how we compare our sounds. Because again, it's the decibel scale is a quantity. Think something you can measure, something you can count. Where when you're talking about loudness and just saying, oh, that was quiet or that's loud, well, that's just a perspective. So the decibel scale actually puts a number to it. So we can compare it because, again, it's a logarithmic scale that every time you go up 10, it's not 10 bigger, it's times 10 bigger. Where, again, the Richter scale that we dealt with is it's smaller. It only goes up by ones. There we go. So I actually experienced an earthquake about a 4. It's kind of neat. You got shuffling in your chair, and my water was bouncing on my desk, but it was definitely a weird feeling. All right, so